We erase the side and proceed to Laplace transform star B. Yes, I erased the star B, but no, not there, star B. Now let's do M of star B. So star B is y prime of t. Y prime becomes y prime bar. Equals. C transpose is a constant row vector. In the vector case, constant vectors and constant matrices factor out for Laplace transform. So that C transpose factors out, and I'm left with Laplace transform of x prime What can I do with that? With the implied assumption.
Make it a steady state.
With the implied assumption, yeah, okay, that's the implied assumption. But with the implied assumption, I have this situation. Even though that may not really be zero, I'm assuming it's zero. So with the implied assumption, this becomes, as Brianna said previously, okay? Very much like we did in the simple example. So, call us double star B, and plug in the x prime bar bar from double star A. So, combining double star B and double star A, we get y prime bar equals C transpose. I have Si minus A inverse B u prime bar, and don't forget A to the minus ds, plus C transpose Si minus, right? And then I have this or sum. E to the minus ds is a scalar. Scalars, remember, I told you, when I have matrices and vectors, the order is extremely important. There's only one type of quantity we can freely move to the left and to the right of any matrix or vector, and that's a scalar. Since e to the minus ds is a scalar, I can move this before the u prime bar, and I can move it here before the di. And I now have y prime bar equals C transpose Si minus A inverse B times e to the minus ds times u prime bar plus the sum of. Also, I can move the C transpose, the constant, inside the sum. Constants can be moved freely inside or out of the sum. So move that also inside the sum. So sum I equals 1, supposed to be a 9. 1 of C transpose Si minus A inverse gamma I e to the minus ds di prime. We've done examples. We know C transpose is just numbers, A is just numbers, identity is just numbers, B is just numbers, D is a number. So, what is this box? All numbers and S. What's the size of this box?
Oh,
C transpose is 1 by n, right?
is that GU?
Yes, that's going to be GU. So, C transpose is 1 by n. Si minus A inverse is the same size as A. That's n by n. B is what? N by 1. What's the result of 1 by n times n by n?
1 by A.
1 by n times n by 1? So that's a scalar. Of course, it is minus ds is scalar. So that's a scalar quantity. All it has is numbers and s. It's a scalar function of s. It's our GU of s. This is the general given our formulation of the model, transfer function. Similarly, this quantity here also has all numbers and s. Again, 1 by n, n by n, n by 1. This is my GDI. So, for the general equation, we have that y prime bar is GU of s, u prime bar plus sum of GDI of s, di prime bar. With the transfer function GU is C transpose Si minus A inverse B e to the minus ds, and the disturbance transfer function replaces B by the corresponding column of the gamma matrix. Identical, except B is replaced by gamma I, where I is the column of the gamma matrix that corresponds to that particular disturbance. So that's going to be C transpose Si minus A inverse gamma I e to the minus ds. I do not have the time to do a complete example, but let's do a quick example. Let's assume, questions? Okay, so let's do a quick example. Say I have the model x prime dot equals sorry, I have the u first. Let's say this is the result of step 3. Okay? The homework you get the results later, right? So, find GU of s, and let's say GD2 of s. Since we don't have much time, I'll just do one with the disturbance. Okay? If I'm going too fast, so see everybody right. So we all know how to get to step 3, and this is the example of step 3 result. my C transpose. This is my A matrix. This is the B vector. The first column is gamma 1. The second column is gamma 2. So, G of S, let's calculate that first, is C transpose Si minus A inverse B e to the minus B. I need to calculate Si minus A inverse. So let's do that. So Si minus A is going to be S. Identity matrix has to be the same size as the A matrix. What's the size of the A matrix here?
2 by 2.
2 by 2. So S times 1, 0, 0, 1 minus the A matrix, which is minus 1, 1, 3, minus 2. A scalar multiplies every matrix, a matrix by multiplying every element of that matrix. So S identity is S 0, 0, S minus 1, 1, 3, minus 2. So that is equal to S minus 1 gives me S plus 1. 0 minus 1 gives me minus 1. 0 minus 3 gives me minus 3. S minus 2 gives me S plus 2. So that's the Si minus A matrix. You should all know how to invert a 2 by 2 matrix. I won't ask you a 3 by 3 inversion in an exam, although if it's something really simple, diagonal matrix. You should know how to invert matrices. Review your COT part on that. Definitely no 2 by 2.
Don't you just switch the numbers, right?
Well, it's not that simple, particularly for ISIs. But for 2 by 2, it's always 1 of the determinant times the adjoint. So remember, the determinant of 2 by 2 is product of diagonals minus product of off diagonals. So the determinant is S plus 1 as S plus 2 minus 3 times minus 1. And how do I get the adjoint? You should remember that.
How do you get what?
The adjoint matrix. You should remember that, guys.
You flip it and then it changes signs.
Excellent. Brian says, I flip the diagonals, and I don't flip the off diagonals, but change the signs.
Wait, what is that called?
These are the diagonal elements. So I flip the two diagonal elements and switch the sign of the off diagonal. So it becomes plus 1 plus 2.
What did you say that procedure is called?
Okay? So this is equal to, and I will leave the 1 over the determinant outside. It doesn't help algebra to bring it inside the matrix at all. So I have 1 over, I get S squared, and I have 1s plus 2s, so that makes plus 3s, and I have plus 2 minus 4 for that. Not that we're going to do anything, so it won't affect things, but do you mind very much if I make one change?
No.
If I change that minus 2 to a plus 2, so I have a stable system? Just bugs me. Won't affect anything else. Change that minus to a plus 2, which means here it's plus 2. Which means here is plus, which means here that is minus. What? Wait a minute, no. What did I do?
Oh, no.
Don't do that.
No?
It's too late.
Wrong thing. I should stay minus. I meant to change one of this. Change this to minus 1, sorry. Sorry for that. Stay here minus 2, change that to minus 1. So here, this is minus 2. Another minus 1 here. This stays minus 2, that becomes minus 1. So here, this is plus, and this also becomes plus. So here is minus 3 times plus 1. And here, flipping the sign, this becomes minus 1. So that's all that changes. Okay?
Is that 35 or 3s? That's 3s.
3s. So I'm multiplying this. So I have s squared plus 1s from here plus 2s makes 3s. And then I have plus 2 minus 3 makes plus 5. So plus 5 times s plus 2 minus 1, 3 s plus 2. So that's SI minus A equals. Question? You should all know how to do that, yes. Absolutely must know how to invert 2 by 2 matrix. Don't show up in the exam without.
We didn't learn how to do that. There was
Of course you did.
There was just a program. There's a program for everything. Just put it in here, okay.
I bet your calculator cannot do that.
Oh, my calculator can do it.
Has symbolic? This is symbolic.
It's the TI-CA.
It's symbolic. I don't think it has symbolic.
They're saying they had a program on the computer
Yeah,
that would do
In
this.
Python.
yeah.
Symbolic? Python has symbolic?
I mean, we never had to do it
It's
like
a
that.
test. With a number, you can always do it with a number.
But
But here I have S, I don't have a number.
in
There are
CSS
software
like
packages that will do symbolic.
What they're saying
Math
is,
type
we never
of
had to
math.
do all
One
this
of those
stuff.
that has one of that has a symbolic. MATLAB has a symbolic addition. So there are computer packages that will do symbolic. But certainly I don't think calculators will do symbolic. It's S, it's not a number here. It's a function of S. If it was just a number, you could do it with a calculator.
that's
but-
not what they're saying. They're saying they never learned how to do this because they had a program that would do it with numbers.
In labs class, you never learned how to do the adjoint like matrix.
adjoint?
and find the adjoint matrix and all that. He didn't teach that by hand.
See, you think he didn't teach that?
I think he did.
Oh, Felix knows it.
I remember.
He taught some matrix math, but he didn't teach everything he did.
I know he doesn't teach eigenvalues, that I do know, but there's no way he's not teaching inverse of the matrix with the adjoint. Computationally, of course, Gauss and Gauss-Jordan elimination are better, but in terms of what you need from a theory point of view, you need the adjoint matrix. And there is no way you could do what John is doing if you didn't know what self-adjoint is. Right? I think Range deals a lot with self-adjoint. Alright. Now, I want to calculate that times B or that times C transpose. One of the two is smarter than the other. Is it smarter to calculate first with B or first with C transpose? Let's read the entire problem. We need to calculate GU and GD2. Okay, it's smarter to calculate with C transpose first. Why is that smarter?
Smaller?
Did I erase for GU and GD? I copy. Here. Yeah, here. I'm calculating these two guys. Why is it smarter to multiply this with C transpose first?
Because C transpose has 0 in it.
Thomas says, because I have